Okay. Right, hello. So my name is Phil Aston, and I'm going to talk today about the integration that I've done with a customer between two Oracle products, Oracle Event Processing and Oracle Coherence. And this is sort of in the context of distributed event processing. And I called it patterns for distributed event processing because I think that some of the ways that we've approached the problem space aren't particularly tied to the Oracle Event Processing product, but I hope it will be generally interesting. So apparently this laptop is my microphone. So if I start wandering around over here, just point me back at the laptop or we won't get a quality recording. But at least I can't turn the microphone off. So, here we go. I've split this into three rough sections. I'm going to do a brief introduction about the two products and the problem that I'm trying to solve with them. And then the bulk of the presentation is around continuous aggregation of events. So we've got a stream of events coming into the system, and we want to sum up information in some way across those events. And if we have time, I have a few more slides on some of the ways that we've found work when you're making the two products work together. And implicit in that, we'll probably talk about some of the ways that don't work. So this is my easy starter for 10, Coherence. None of this should be news to you. I haven't. I've sort of assumed a moderate knowledge of how Coherence works, particularly around partitioned caches. Hopefully you can sort of fill in the blanks and things that I'm not spelling out. I think the main message to say about Coherence is it's not an event processing platform. It's a data grid. So although this might be conflicting with Noah's talk later on, where he'll show you how to take Coherence and do event processing with it, I think there he's plugging in other technologies as well, whether it's WebLogic Server or WebSocket. So I'm quite interested to see what patterns he's found. So to sort of perhaps make this a little bit more concrete, if you can imagine when you're processing events, one of the things that you quite commonly need to do is join two event streams. And that means you're hanging on to one event while waiting for another event to arrive. So how are you going to do that? If you do that with the server-side event notification mechanisms, well, you can't do that because you can't block server-side threads or your cluster will just grind to a halt. And if you're doing it with client-side map listener type things, well, you then lose some of the atomicity that Coherence would otherwise provide you. But it's a great data grid, and we can lean on it for the atomic changes, for the scalability. I don't know how many of you were at the last SIG, or how many of you managed to see Andy Piper's presentation on Oracle Complex Event Processing, CEP. It's been renamed recently by marketing to Oracle Event Processing because it's obviously not complex. And there he went into sort of the product in some depth. I'm not going to, so again, you'll have to sort of mentally sort of fill in some of the blanks, but hopefully I can give you enough detail here to get a flavour of what the product is about. So the way I like to think about it is it's really an application server, primarily, that's sort of focused and tuned for event processing. It's built on OSGI. The programming model is a mixture of Java and Spring, and it has this concept of a event processing network, which its tooling, its IDE support lets you visualize and easily wire things together. And the event processing network is composed of adapters, which sit at the endpoints of the network, and either input adapters, receiving information from maybe coming off a message bus, or they might be listening to triggers in a database or to sockets, however you want to implement it. And there's a few out-of-the-box adapters, or you can write your own, the very simple Java class, to produce events. And you have a network of channels and processors as the events flow through the system. and at the other end you have output adapters which clearly publish them. And typically you have a high volume of input events, you're adding some value in the middle and producing a low volume of more significant output events on which you can take some action. There's a special type of processor which you can put into your network called a continuous query language processor. And that uses a declarative language which is a bit like SQL, but lets you deal with event streams. So it lets you join event streams, aggregate events, project them, and generally do set type operations on a stream of events and over time. So you can say things like, find me the highest value in this stream of events that's occurred in 5 minutes, and fire off some event whenever you see that. So every 5 minutes you'll get the highest value published. Or join these two event streams by this key and produce some composite event. And so whenever you see matching events come in, an output will come out of that. So this is quite a powerful feature of the product. And there's pretty good coherence integration in the product out of the box. So if you create a cluster of the event processing servers, check I mentioned this. So as well as being Java and Spring based, the actual process is, and the environment is an OSGI environment. So the applications that you deploy are OSGI bundles. So an OEP server is a JVM. And if you wire up a set of these into a cluster, the product uses coherence for that member discovery and distribution of configuration. It has all of the support for being able to easily put coherence cache configurations into your application, package them into bundles and deploy them, and it does all of the detail work about making sure that the class loaders are all set up right. It's easy to publish information into a cache from the EPN, so there's out-of-the-box adapters that will automatically let you flow events into caches, and you can join from caches. So as events come in, you can enrich those events by saying, okay, pull this information out of this coherence cache and put it into an output event. The thing it doesn't do very well is it doesn't really help you with a distributed event processing problem. So what do I mean by a distributed event processing problem? Pretty much one that doesn't fit into a single JVM. So if you've got lots and lots of data and you've got to split that data stream up so that you can fit it into memory and process it, that's really left as an exercise for the user. It does have support for high availability capabilities within a cluster, so you can set up multiple processes and you can link them together in a way that they're essentially doing exactly the same calculation, seeing exactly the same streams coming in, calculating exactly the same results, but you can link them so that one of them is the master, and if that dies, then another one will take over and continue to produce the same results. But if you do that, your problem still has to fit into one JVM. So what if the problem doesn't? So this is sort of background to the problem that we're trying to solve here. So what I'm assuming here, I've tried to make this, it's a little bit abstract, but I hope through doing this you'll sort of see the general principles coming out of it. So I'm assuming that there's an event stream, and every event is represented by this little schema here. So you've got some key attributes, A, B, and C, and some value. And you want to do some kind of operation against it. So this looks like SQL, but it's actually some CQL. And it says, select a couple of the keys and the sum of the value from the event stream grouped by the keys. So we're trying to just split the distributed stream of events into little partitions, sum up those partitions, and produce a result. And we've got a big data set, so we want to make use of a whole cluster. We want to do it in a distributed manner. We want it to be efficient, So that means not having to have a lot of chatter across the cluster as we do it. And I guess I could also add scalable to this, and we want it to be resilient. So here I'm sort of looking, think about this as coherence style ilities. We don't want to be writing things down to disk to achieve the resilience. We want to have, we want to do as much as we can in memory and rely on other nodes backing things up in memory to achieve the resilience. Okay. So we've got a large volume of events. I've sort of hinted at this before. And the events are streaming through the system. We can't fit it into one memory space, into one process, so we've got to shard it or split it up across different processing partitions. And here, just a very simple diagram showing we're doing some processing on the input, and at each processing partition, we're calculating or accumulating part of the answer. So there's two things going on here. We're splitting the events up, dividing a third of them to each partition. We're producing a third of the result here, and then we're accumulating the result to produce some kind of total result. So however we do this, however we solve this problem, this partitioning, it has to be somehow fundamental to it. Typically, I think we'd also have, in all the problems I'm looking at, and in the, I think this is quite fundamental as well, that events normally, they represent changes to some kind of identifiable entity. So they're either saying, okay, here's a new version of, this is the first time you've seen this entity, here it is, or here's a change to this entity, or remove this entity, it no longer matters. And because of that, within the system, you've got some kind of representation of that entity, the events are coming in, and you're really interested in the differences that are going out. So the system that I've been working on for the past year is a trade processing system. We're taking real-time streams of trade and risk information and doing accumulation across it. So this value here might be something like the market value associated with a trade, and you're going to change that market value, and so you know what the old value was. You really want to push the difference on. So all I'm getting at here really is that there's logically 3 different levels of aggregation that you might be interested in. So the entity level, the processing partition level, and the final result. And you can look at this from 2 different ways. If you're doing true event-driven aggregation, continuous aggregation, where your events are flowing through your system, that's kind of a push model. So a single event here might affect a single entity, might affect the end result at a processing partition level, and then contribute to the total. Or you can do what's a query model, a pull model, and this is exactly what you'd do with a coherence entry aggregator. You send a request to the system, and it goes and pulls the information from all of the entities and aggregates up at the various different levels. This requires that you've actually got the value stored there that you can go and query. Actually, with an event-driven aggregation, you don't even need to store the value. You can just push the change all the way through. So I see a new event. All I need to do is remember this total here, and it flows through, and we total it up. But it turns out that actually it's usually quite useful to have the value stored at this level and stored at this level, because with a continuous aggregation, you've got to know the thing that you're querying ahead of time. You set up this filter, you set up the system, it's receiving these events, it's doing the calculation, and pushing the answer. So if you know, yes, I want to group by these attributes, so I want to do this particular type of calculation, you can set that up, you've got a machine that does it, then you fire the events at it. Great. the advantage that you have with queries, you can do an ad hoc query. You can go and say, okay, actually, that's not quite the answer I wanted. I wanted to do this, and you can send the request back to the system, get the answer. So you can also end up with hybrid models here. So here we're showing, well, we're not pushing the event directly to the end user. What might that be? That might be putting the result on a message bus or pushing it to the end user's browser. We'll actually store it, and then the user can come and query it. Okay, so let's just look at the two products and what they can bring to this particular problem. So Coherence lets you do this aggregation by query using an entry aggregator. And it's powerful. You issue it, churns on the grid, gives you an answer. But every time you want that answer, you've got to go and get it again. It's got to do that calculation again across the whole grid. It also has this feature which you sort of initially think, oh, maybe this is useful for event processing, the continuous query cache. And despite the name, it's continuously being updated, it's not an aggregation mechanism. It's just really a way of getting a view, an up-to-date view of a particular subset of your data out at an end client. So the entry aggregator is kind of useful, but we don't really have a continuous aggregation mechanism here. In OEP, we have continuous aggregation, but not aggregation by query. So here's that aggregation again, and it's continuous, so that whenever a particular event arrives, say at the CQL processor, it only needs to update the particular bucket A and B, which that event applies to, and that little tick just changes that number and moves on. So as all the events flow in, you're only touching the thing that changes. And the engine is smart enough to be able to evaluate multiple events coming in multiple threads. There's not sort of a single synchronization point. It will update all of these little numbers it's got for each of the pairs of A and B and accumulate the final value. And the engine also supports user-defined aggregations. So this doesn't need to be a simple arithmetic sum. It can be anything you like. So to give you an example from the system I've been working on, we have trade information, trade messages coming through, and one of the things we're interested in is bad data and how much bad data, how many of these trades are bad, how many of them are good, and so we do various types of validation rules on the fields that come through, and we total up in a little map. Okay, you've got n of these, y of these, and we build up this composite map that tells me how bad that particular slice of data is. So we might be summing up that over a particular processing day and a book's worth of trades and producing these little views to say, yes, okay, well, that's really bad data, or no, this is clean. And it gives you that real-time view of how good or bad the data is. So this is all good, but it's only within one process. And the challenge here is that it's hard to make make it resilient. You're building up a lot of state. Every process is seeing a slice of the data. It's accumulating these numbers. If you're just doing pure CEP processing, you probably also have a relation of all of the trades that you've seen so far there in the engine. And there isn't anything in the product that lets you sort of magically replicate that and duplicate that elsewhere, back it up, without doing exactly the same calculation on a peer process. So that's a challenge. So it turns out if you combine the two products, you can get the best of both worlds. So fairly obviously, the processing partition, we aligned with the coherence partition model in a partitioned cache. And that gives us a few things for free. It gives us the ability to cheaply join related events through key affinity. So we're joining streams of trade and risk information. The risks know what trades they apply to. We flow those all to the same partition, and they're immediately there on the same process. And coherence is dealing with the transport layer for us, if you like, and the routing that happens there. We can use partition-level transactions to make sure that as we're making changes across that set of data, that they're being done atomically to the storage. So we store the actual data, the information about the entities in coherence, and we don't keep separate relations in OEP. So that's one set of state we don't need to worry about in the event processing product. We just rely on the robust coherence support for managing the data. And as a side effect of doing that, that means we can also query that data easily. We can run aggregation by query against the grid, as well as having this event processing layer running on top. But we use CQL within each process to do the partition-level aggregation, and that gives us this quite expressive declarative event-driven framework. So, a little bit of the detail here. You can see some of this at the back. Let me just walk you through this. So I've split this diagram horizontally into two layers. The top layer is sort of the OEP view of it, and this is a little slice of our event processing network. So we've got events flowing in from left to right. We're doing some processing on these events. It doesn't particularly matter what at the moment. Maybe this is the validation processing that we do. And we have an adapter at the end of this first processing chain that publishes the change into coherence using an entry processor. So the entry processor puts the entity into the cache and perhaps calculates a little aggregation. So again, this might be the map of how many particular types of error we have. And that means we can use entry aggregators to do aggregation by query. And as a side effect of that, the entry processor also fires out an event to the next part of the event processing network that represents the change to that entity. So it calculates the change, the map has changed by this much, and pushes the event down to the second part. Then I've got some of this is nearly the real continuous query language that we use. And it's sort of split into two parts here. So here, this first part looks relatively familiar to the logical view that I showed earlier. So we're just doing a select, some keys, an aggregation, and a group by. And every change that comes into here will be making a change here. Tick, 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 tick. This is sort of logically a relation. You've got a number of values in memory, and every tick will both say will fire off a change to one value in memory that says, okay, the old value was that's gone. Here's the new value. And this iStream operator says, actually, I'm only interested in the new values. Forget about the old values. That's history. We don't care. But what we can't do is to fire off events to the total aggregation, and we're aggregating across all of the partitions for every tick that comes in. That just wouldn't fly because it's a network operation. So we've got a second half to this query here, which sums up over 15 seconds. This is a little bit cryptic, but it's saying, okay, select from this view, from the totals view, over a 15-second period, and take the last value every 15 seconds and publish that, because it will be the highest value. So we've got some sort of free buffering mechanism just by using the engine. And then for the final aggregation, to produce the final result, we actually just push these values into Coherence. So we've got a value for each partition in Coherence, and we just run a query against that. And that's really because we don't have a sort of an event-driven endpoint at the moment. We're taking a real-time stream in, and we're not at the moment publishing a real-time stream out. So we want to be able to just come and query what the current values are, and we can query those from Coherence. If we wanted to have a real-time output, then we could have another stage of CQL which sort of summed the sums. So that's all well and good, but we still haven't quite solved the resilience side of it. So go back here. What happens when this goes away, when Coherence fails partitions over? So we don't really care about what happens when Coherence fails partitions over, when you lose a partition, because if you lose a partition, wind back, no, we do care about that. We don't care about what happens if you lose a process, because all of this is in the same process. So the common thing to think about is, well, what happens if I'm receiving partitions from backup? If a process has failed and a backup partition is suddenly reconstituted and I've become the new owner of it, I've suddenly got a big stack of data to deal with. And I do care about the other way, losing data, because we might be starting up more nodes in the Coherence cluster, and I might be giving away partitions of data to other nodes. And so really it's a problem of making sure that the state that's here, that's atomic and has Coherence quantity of services, is managed to a Coherence quantity of service, is synchronized with the state that's implicit in this little node here. So, I'm going up or down? Yeah, so this is how we go. So, our processing partitions are Coherence partitions. So the first thing we do is we make sure that each processing partition produces an absolute result. And that means that if we fail over and a new node calculates a new result for that processing partition, the total result is consistent, or at least eventually consistent, after a new value has been published. And then within the nodes that are receiving new partitions, we use a backing map listener to track that event. I've got a diagram here, might make it a little bit clearer. So we're publishing results, and as usual, the change to individual entities are being pushed up through the VPN. But if we suddenly end up owning a new partition, a backing map listener says, oh, okay, right, we're now responsible for all of these keys, queues them up, and the scheduled entry processor then pulls out the current totals and pushes those through as absolute totals to the new aggregation. Am I losing people here, or are they? No? Okay. And then you see the other piece of detail that I've added to this is that we're tagging every result with the partition ID, and that lets us, when we sum, when we split it up and have it all tagged by the partition ID, the new owner basically overwrites the stale values from the node that has lost the data. Okay, so that's the basic pattern that we've used to do this continuous aggregation. I want to talk a little bit about another piece of the puzzle, which is the interaction between Coherence and Oracle event processing. And probably the thing at the heart of this is that there's two threading models here. There are Coherence service threads, and if you're doing any server-side programming with Coherence, you know that the one thing you absolutely can't do is block a service thread to do some external I/O, or these are not cheap things. If you have a small number of service threads, per service, and if you start waiting for tens of milliseconds in them in the service threads, the whole coherence asynchronous kernel mechanism will just suddenly grind to a halt. So anything you do in these threads needs to be quick and reliably so. And then the other pool of threads that we have at our disposal are the Oracle event processing threads. They use, they're built on technology that comes from WebLogic Server. They have a sort of a self-tuning thread pool that dynamically adapts itself based on the throughput that it's measuring, of how quickly it's processing requests. And so if you are I/O bound and you're waiting on endpoints, you're waiting on the database, then the thread pool will grow the number of threads that are available for processing. If you're CPU bound, it will shrink them. So this is better for sort of longer running operations. We have a sort of an interaction between this, because up at the front we've got an OEP thread taking a request in. We then need to do some processing on that thread. Then we're pushing it into Coherence, at which point we're going to be using a service thread. That's changing an entity, and we want to then link that back into OEP in a reasonable way, given that the next step of processing that OEP does may be blocking on a database or whatever. So we've got quite a strong rule of thumb here that says whenever you dispatch to the event processing network, every dispatch that you do from an event that occurs in Coherence can't result in an I/O. It's okay if 1 in every 1,000 blocks for a little while, but if it's sort of one-to-one, then even if you put an asynchronous channel in between, so that you're doing that handoff between a Coherence thread and an OEP thread, if this takes 10 milliseconds to process everything, then this buffer, this blocking queue will fill up, and you'll start blocking Coherence threads, and that's bad news. So, but if not, and that's the case in our aggregation, because we're, as you saw, we're buffering things up, so we're only publishing a result maybe every 15 seconds, then it's perfectly okay to use this asynchronous channel. This is a configuration thing in OEP. You say, right, I want a channel here. This operation, this thread pushes the event into the channel, and a separate OEP thread pulls things off. So this is very quick. The only time this isn't very quick is if that gets to its maximum size and you get blocking. So if you know that, it's fine. It's fine if you know that the number of times, the average wait time here is going to be very small, then it's fine to do this. Otherwise, if this is a more one-to-one relationship, if everything that this does is going to result in an operation here, don't use an entry processor, don't use a server-side thread, have the OEP side of it synchronously poll using the name cache API and pull the information out of the cache. So a couple of other points. There's one final slide that I wanted to get to, but a couple of other points just to add a little bit of colour to that. The other thing that I've sort of not talked about yet is how to do that distribution. We want Coherence to distribute the incoming events according to its partitioning, and then for efficiency, we want to keep the processing of a particular event on that JVM. We don't want to be sending the messages around the cluster. So how do we do that? And this is quite unusual actually for a Coherence system, that we're sort of combining the processing with the storage. But that lets us keep this flow of events. They get distributed once when they come into the system, when we're pulling them off, in our case, off a message queue. They flow into a cluster, and then they stay on that JVM until they exit the system. And the only I/O that we're doing other than that initial distribution is to make the backups for the changes that we're making to the storage. And I'll talk about this second point later, so let's get to the diagram. So right up front, we have this thing called the queue cache, and we have an upstream piece of our event processing network, which has adapters which take the incoming events. This is actually, as I say, pulling off a message bus. We have a queuing adapter, and all that does is put the event into a partition cache. And within the partition cache, we have these little mini queues of things that are coming in, events coming in for that particular partition. In fact, we've gone to a finer level here. The queues are actually for a particular business key. And then on the other side of that, we do this scheduled poll, which is pulling off information out of a particular partition. And this is focused and local because it says, okay, I know I own these partitions. I only need to go and query these 3 partitions, and pulls the events out in order and pushes it to the downstream EPN. And that can we do another thing here. We also make sure that for a particular partition, there's at most one active thread pushing the event to the downstream EPN. And that means down here, we don't need to worry about race conditions. The order in which the events go into here will be the order in which they get processed here. And that's freed us from a lot of otherwise irritating problems between 2 different events arriving for the same trade and dealing with them both changing the storage at the same time. Okay, so the final point I had on this was just around the backup and the replay. Every event that comes through this is coded to be to make idempotent changes. So should this go down and fail over, the recovering node can replay the events from this queue and not have side effects that we weren't expecting. So it will just make exactly the same changes from these events. Okay, so I can stop now. I appreciate I've talked across what's quite a complicated system quite fast. You've all been very quiet, so I'd invite some questions. Go back from the queue cache to the actual. So this, I guess, is the heart of it. Any questions? Okay, you're all obviously very hungry. Oh, there's one at the back. Rob.
Quick question. So you mentioned that you configure a backing up listener to handle the case of incoming transfer from your responsibilities on the server side, right?
Yep.
If I understood you correctly, configure a backing up listener and you get events for every key that's inserted.
Yeah.
Use that, I assume that set of keys to queue to an entry processor which fire out asynchronously to go back and process those new responsibilities?
Yeah, exactly. So so if suddenly own a new partition,
Yep.
we get called back on the backing map listener for every key.
Yep.
The backing map listener is something you definitely don't want to block because you'll be blocking all processing for that service on that node. And so we essentially just note those queues in an in-memory structure. Doesn't really need to be resilient because if you fail, somebody else will recover.
Right.
And we have this entry processor that regularly looks in that in-memory structure. It's essentially just a queue. So, okay, I have these, and so this entry processor pulls them out and goes through the same route. But it knows, unlike in this case where you're actually firing a change and you've got to fire a delta. In reality, this is a negative event and a positive event. It's saying, okay, this is the old value. I'm deleting that, and and this is the new value here it is. So if this was, say, a market value, might be gone from $100 to $150, it would say, okay, minus 100, and then another one comes through plus 100, and it all comes out in the wash here. And in this case, it's going to be an absolute value because it's whatever is the current value in the entity.
Got it. So that entry processor that's on the side, is that whose thread is that running on? Is that
it's an entry. There's a scheduling process that will be triggering this off, and it's a client-side OEP thread that will be triggering this regularly. But because it's an entry processor, it runs within the context of a service thread. So that's a coherence thread, and then separately there's a timer that triggers off one of these, pulls a batch of things out, and processes them.
Quick one. That delta PID that you carrying from the entry processor, is that a pull from that queue, or is the entry processor publishing that event?
So it's the entry process. So there's two things going on here. This bit is about the recovery.
Yeah.
This bit is the normal flow. This is where most things go through, and this is the entry process. The thread that the entry process that mutates the cache also then calls downstream.
But what is the cost of that operation?
So that's really, if I'm just going on, that's really the cost to take the message, which is a Java object, and put it into this blocking queue. So it's only going to be costly if that blocking queue is full. So normally it's very cheap. There you go, I'm done. And so that's what I was the message I'm trying to get across here. You're okay so long as you win the numbers game, and the race between how fast you produce events here and how fast you consume them here. If you start to lose that race, then you very quickly see the system.
But that's when you have that multi-threading processing all that.
Yeah, so we can use multiple threads here, and you can pull from here as fast as you like, but you have to absolutely make sure that you don't block on a database or something. And
I have two questions.
Okay.
One's a very basic question. I'm sorry for being a bit slow. Are you running complex web processing engine in the same JVM as the Coherence?
Yes.
Has that affected performance of Coherence? Have you had any issues with the Coherence tends to be a bit sensitive to value behavior JVM?
So I'd say the behavior is stable. The throughput is an ongoing. We're really targeting throughput here, and how the rate of messages we can push through it. The throughput isn't as high as we'd like, but every time we look at it, we find it's probably the main cost is the cost of serializing and deserializing things backwards and forwards from storage. The scalability is good. We halve the number of nodes, we get half the throughput. And it's hard to see how, because the flip side to it would be that you would be having this conversation between a separate event processing system and some storage, and you'd just be doing a lot of network I/O. And the only way you can make that go fast enough is to batch it up, and batching is kind of the enemy of event processing. It's hard to play one of it off against the other. So we've aggressively gone for this do it all in process approach. And and a lot of counterintuitive things, like actually we found that reducing the thread count and reducing the amount of context switching that's going on is usually the way to go.
JRocket does a good job as well.
Yes, so it's all running on JRocket, and so it's not a garbage collection problem; it's a CPU problem, and that's mainly driven by the amount of serialization that's going on.
The other question was around partition moves. Can you just bring up the diagram again?
Sorry,
The partition moves when you're recovering from a partition move.
okay, so this one, wrong way.
That one.
Yep.
You're not going to raise condition there between the new absolute value coming out and the delta coming out. How did you get around that?
Right, yeah. So what we do there is, you're absolutely right, there is a race condition there, and the thing that publishes here checks whether there's something in the queue and doesn't publish a delta. Okay. So it just mutates this, and the entry processor will eventually catch up with it. Okay, yeah. So paying attention anyway. Okay.
What is the number of events that you can actually process in this model? What are you seeing?
So we're seeing maybe something like a few thousand per machine, which is per second.
Physical machine or virtual?
Physical machine.
What sort of machine are we talking?
Modern, something like yeah, 12 I think, isn't it? Yeah, and we've done a little bit of playing around, and our biggest wins are changes to our model, so that we're doing less serialization at this point when we're mutating this. So we're doing quite a bit of path, but at one point we had say trade and risk information flowing into the same cache, and that into the same cache entry, and now we've got sort of a separate substructure for the risk information, which just grows and grows and grows and grows. So we put that into a subordinate cache. That made a big difference. Okay, I think I can probably call lunch.
No, I'll stay for it.